Hi, once again. Okay, so this is serious math. Okay, so we'll be discussing first order applications of differential equation or applications of differential equation, particularly for logistic growth and linear modeling. Okay, so we have a couple of examples. So one for logistic growth and another for linear model. So we'll start with logistic growth. Logistic growth refers to any type of growth that exhibits a steady expansion, followed by an abrupt slowdown. So there are various phenomena that can follow a logistic growth, such as industrial growth or population growth, spread of resources, or human or machine learning. So those are examples of logistic growth. Graphing it, okay, so over a certain period of time, so the growth of that certain parameter follows these. Okay, so at a certain period of time, so there is a gradual increase, okay, on a certain logistic, and then it increases abruptly. However, so there will be such a time that it will reach the carrying capacity of the logistic, and then there won't be any changes anymore, or there would be a minimal changes. Okay, so for a given logistic growth. Okay, so this is in difference with that of the exponential growth. So in an exponential growth, so it increases until an infinite number. Okay, so while for a logistic growth, so there is a gradual increase for some time, and then for another time, so there will be an abrupt increase or an abrupt growth on a certain logistic until it reaches a certain point. Okay, so which is the carrying capacity of the logistic, and it maintains that value, or it doesn't change anymore. Okay, so let's have an example pertaining to a certain logistic growth. Like for example, a college dormitory houses 100 students, so each of whom is susceptible to a certain virus infection. So there are only 100 students in a dormitory. So a symbol of epidemic assumes that during the course on an epidemic, the rate of change with respect to time of number of infected students I is proportional to the number of infected students, and also proportional to the number of uninfected students. So if at time 0, a single student becomes infected, show that the number of infected students at time t is given by I is equals to 100 e raised to 100 kt divided with 99 plus e raised to 100 kt. Okay, so this is a logistic growth. We are given the number of students, which is 100. So initially, one of the student got infected of a virus, but then the relation on how or a model of epidemic provided us a relation that the rate of the infected students, okay, is directly proportional to the number of students infected, and at the same time proportional as well to the number of students are uninfected. Okay, so to resolve this one, so we assume, or we let some values here. So that is, so we let, so let's say I, okay, so corresponds to the number of students that are infected by virus. And then since there are 100 students, so if I corresponds to the number of students infected, so therefore the number of students uninfected would be 100 minus I. So number of uninfected students. So if I would be the number of students infected, so a total of 100 students are there. So we subtract the infected, so from the total, so that's giving us the number of uninfected students. So next, so we have our given that initially, so when time is equals to 0, the number of students infected is only 1. And then how will it spread? Okay, so to other students. We are given already, okay, so the working equation on how to predict, so how many numbers of students will be infected after certain time. Okay, so after certain time, so which is I is equals to 100 e raised to 100 kt over 99 plus e raised to 100 kt. So what is required? So we're just going to prove. So prove that I is equals to 100 e raised to 100 kt all over 99 plus e raised to 100 kt. So for our solution here, so we draw our equation. So from the problem, so it says that the rate of change, okay, so with respect to time, the rate of change with respect to time of number of students infected, I. Okay, so the number of students infected is I. So therefore, the rate of change of that is di over dt. And then it says that it is proportional to the number of infected students. So proportional to the number of infected students, so which is I. So proportional to the number of infected. And also, so when we say and, so that is multiplication. Okay, so and. If it is or, it will be plus. So and is multiplication, and if it is or, it will be a sum. Okay, so it is proportional to the number of infected students and also proportional to the number of uninfected students. So ano yung uninfected students? So that would be 100 minus I. So this is our variation. di over dt is proportional to I times 100 minus I. So now to make this a differential equation, so we introduce proportionality constant. So di over dt will be equal to k, our proportionality constant, times I, 100 minus I. And giving us the differential equation. And based from it, okay, so based on it, this is a separable equation. So we can make this one as di all over I times 100 minus I, then multiply it with k dt. So the right side of the equation can easily be computed, but on the left hand side of the equation, so we can compute that one, so using partial fraction. So this is the same as 1 all over, so I times 100 minus I. So the two factors are I and 100 minus I. And then both are linear. So therefore, we have A and B. So we multiply everything by I times 100 minus I. So giving us 1 to be equal to A times 100 minus I. Then plus B, multiply it with I. So now we can substitute. So to get for the value of A, so we assume for the value of I, that when I is equals to 0, so what happens? So this is 1 is equals to, so A, 100 minus 0, so here, 100 minus 0, it's still 100. And then B times 0, it's 0. So therefore, A is 1 over 100. And then, so to solve for the value of B, so we assume that I should be equal to 100. So we write 1, and then 100 minus 100, so that will be 0. So eliminating A, and then B, I is 100. So thus B is 1 over 100. So this time around, so we can rewrite our equation, so to be, So it's di. So our a is 1 over 100. So 1 over 100 divided with I. And then our b, so plus b, which is 1 over 100 divided with 100 minus I. Multiply it with di is equals to k dt. So now we can integrate both sides. So this would become di over I, which is ln I, or 1 over 100, so ln I. And then this one would be 1 over 100. Our denominator is 100 minus I. 100 minus I. So once we derive it, it's negative di. So therefore, our neutralizing factor would be negative 1. So that would give us negative 1 over 100. And then ln of 100 minus I is equals to kt plus c. And then we remove 100. So by multiplying everything by 100, so that would give us ln I minus ln 100 minus I is equals to 100 kt, and then c times 100, it will still be c. And then so we perform, or we apply rules of logarithm. So this is minus, so we can combine them as ln of I over 100 minus I is equals to 100 kt plus c. So again, so we exponentiate both sides, so leaving us to have I all over 100 minus I is equals to ce raised to 100 kt. So now we find the value of c. So that is, again, so when time is equals to 0, there's only one student infected. So when t is equals to 0, I is 1. So we substitute I is 1 all over 100 minus 1 is equals to ce 100k time is 0. So e raised to 0, that would still be 1. So therefore, c is 1 over 100 minus 1 is 99. So we substitute. So I all over 100 minus I is equals to 1 over 99 e raised to 100 kt. So we transpose, no? So the 99, it will become 99i. And then the other one, so will become 100 minus I. Multiply it with e raised to 100 kt. But we need to express what is I in terms of k and t. So therefore, we need to combine I. So we have two i's, this one and the one on the right hand side. So that is why we distribute. So 100 e raised to 100 kt, then minus I e raised to 100 kt. Then we transpose. So 99i, and then plus I e raised to 100 kt is equals to 100 e raised to 100 kt. So we factor out I, so giving us 99 plus e raised to 100 kt is equals to 100 e raised to 100 kt. And thus I then will be 100 e raised to 100 kt all over 99 plus e raised to 100 kt. And that will be our task. So which is to prove that I is equal to 100 e raised to 100 kt over 99 plus e raised to 100 kt. Okay, so which is this one. And we can already use this working equation. So let's say for after some time, okay, in this case it was no longer specified what would be the unit. Okay, so for time. And then, so we can use this model. So in predicting, so how the virus, okay, so will infect students within that dormitory. Okay, so this is an example of a logistic growth. So next we have linear problem. So for linear problem, so typically the differential equation is already given. So we just, or the linear model is already given. So we just need to understand how it works. So by applying the methods of first order differential equation. So let's say in this case, we are given an equation about the forgetfulness or on how our brain works. So it says here that when forgetfulness is taken into account, the rate of memorization of a material is given by this one. So dA over dt, okay, so is equals to K1 times M minus A minus K2 times A. So we're in here M, okay, so M is the total amount of the material to be memorized. Okay, so let's say you have an exam, the amount, okay, of the material that you need to memorize, so that corresponds to M. And then since you're going to study, okay, so you're going to memorize, so A naman, so corresponds to the amount of the material memorized at time t. So that means A is the amount that you already memorized. So M is the total amount that you need to memorize. So therefore, the difference between the two, the M minus A, so corresponds to the amount remaining to be memorized. So that's the amount remaining to be memorized. And then the negative or the minus K2 times A, that accounts for the fact that you're going to forget something. Okay, so it doesn't mean that you memorize, so that one will retain. So there is a possibility, okay, a higher possibility that you are going to forget something. Okay, so out of the material that you memorize. So it follows that the more rapidly we forget, so the more we memorize, the more rapidly we can forget. So initially, you know nothing. Okay, so you don't know nothing about the material that you are about to memorize. So we are just to prove that the material will never be completely memorized given that K1 is greater than 0 and K2 is greater than 0. So we have two proportionality constant, so K1 and K2. And it says that K1 is greater than 0, okay, and K2 is greater than 0. It only tells us that K1 and K2 are both positive. So for the given problem, so we are provided by a hint as well. In short, we are just going to find what is A as time approaches to infinity. Okay, so what is A as time approaches to infinity? So in this case, we don't need to provide our given. So since we are just to solve the differential equation, so right away we can write our equation. That is dA over dt is equals to K1 M minus A, or M minus A, and then minus K2 times A. So we just need to find what is A versus time. So we just solve, we just find the solution for this equation. So later on, we'll try to understand how it works. So dA over dt. So we have two variables here, so which are which is A. So we need to combine. So we distribute K1. So that will be K1 times M minus K1 times A. Then minus K2 times A. So we combine. So that is K1M. And I could factor out negative A. So this one will become K1 plus K2. Negative K1 plus K2. So now, so dA over dt, I'll transpose that as K1 plus K2 times M will be equal to k1 times m. So from here, so we can see that we have a linear equation. Okay, so it's a linear equation, linear in A. So this should be k1 k2 times A. So this is linear in A. So our P of t will be k1 plus k2, and our Q of t is k1 times m. Okay, so only A and t are considered to be variable. So therefore, we use our formula in solving for the integrating factor, that is pt dt. So E then is to the integral of k1 plus k2 dt. And so from here, so we can get that the integrating factor then will be e raised to k1 plus k2 times t. Okay, so for our integrating factor. So now we compute for the solution. So that is mu of t. So this is linear in A. Is equals to q of t, mu of t dt. Mu of t is e raised to k1 plus k2 times t. Then multiply it with A. Qt is k1 times m. And then e raised to k1 plus k2 dt. So this is the same as e raised to k1 plus k2 times t. Multiply it with, I'll start it with a, then it's equals to, so k1 and m are constant, so we can move it out. So k1 m integral of e raised to k1 plus k2 dt. So from here, our u, so this is an integral of exponential function, so u is k1 plus k2. Our du then would be there should be a, it's not dt, that is t. K1 plus K2t, and then we have dt there. Okay. So K1 and K2 multiplied with t. So therefore, our derivative here is K1 plus K2 dt. And since that is dt, so we need a neutralizing factor of 1 over K1 plus K2. So since we don't have K1, K2 for the coefficient of the exponential function. So thus, our integral then is a e raised to k1 plus k2, so multiply it with time, is equal to, so k1 times m, and we start with the neutralizing factor of 1 over k1 plus k2, and then that is e raised to k1 plus k2 times time. And then of course we have the plus c. So giving us to have a e raised to k1 plus k2 times t is equals to k1 m over k1 plus k2, then e raised to k1 plus k2 times time, and then plus c. So now, so we can get a, so we can multiply everything by the inverse of exponential function, e raised to negative k1 plus k2 times t. So that would cancel out, okay, our exponential function at the left hand side. So at the right hand side, it would cancel out that one as well. So k1, so we can have k1 over K1 plus K2 then. So multiplied it with them. And then plus C e raised to negative K1 plus K2 times T. Okay, so this is our working equation now, that the amount of the material that we memorize, okay, or that we can memorize would be K1 all over K1 plus K2 times M, and then plus C e raised to negative K1 plus K2 times T. Okay, so we have to show, it says here that we have to show that whatever we're going to do, we cannot completely memorize the given material. So it's because we're going to forget something. Okay, so definitely we'll be able to forget something. So we can prove that one if we're going to let T to be equal to infinity. Okay, so that is when T is infinity, so we need to find what is A. And that is A is equals to K1 over K1 plus K2 times M plus C e raised to negative, so K1 plus K2 raised to infinity. So in here, so we have infinity, so which is very large number, so multiply it to any constant, so it would still be infinity. Okay, so it's still a large number. A large number, multiply it with a positive number. Remember that K1 and K2 are both positive, so therefore it would still be a large number. But then we have a negative. A large number times a negative, it's a negative large number. And then we have e raised to negative infinity. Okay, so e raised to negative infinity is approximately equal to 0. So even if we're going to do it in our calculator, so let's say you write e raised to negative 1 million. Okay, so the answer will be approaching to 0. So since this is approaching to 0, so e raised to 0 so that would make the given term, okay, so raised to 0. Okay, so e raised to 0, that would just be e raised to negative infinity, that would make it 0. So thus, it only gives us A to be equal to K1 over K1 plus K2 times M. So now, so we can conclude. So what would be our conclusion? So that is, if K1 is positive and K2 is also positive, then we can say that K1 will always be less than the sum of K1 plus K2. So also, if K1 is less than the sum of K1 plus K2, so therefore K1 over K1 plus K2 should always be less than 1. Right? So if K1 is smaller as compared to K1 plus K2, so we will always have an improper fraction. Okay? So improper fraction, so cannot have a value greater than 1. So it's always less than 1. Okay, so if it is less than 1, so multiply it with M. Okay, so wherein M corresponds to the amount of the material to be memorized. So that only means if K1 over K1 plus K2 is less than 1, so that means there is no time, okay? That is, there will be no time T that will allow you to memorize the material M. So there will be no time T that will allow you to memorize the material M. That will allow you to completely memorize the material M. So, in short, there will always be a time that you're going to forget something. So that is why this linear model pertains to a model of forgetfulness. Okay? And that's the beauty of mathematics. So even how our brain works, so we can represent it into a differential equation, so for us to understand how it works. And these are examples of logistic growth and linear modeling problem, so for first order differential equation. And again, that will be all, and God bless always.